Okay, off we go. So last time we were talking about cross products, and we had previously discussed determinants, and before that we had talked about this whole business about right-hand order, left-hand order, clockwise, counterclockwise, all that stuff. Okay. All right, so picking up from there, next theorem, here it is, a really surprising result. When you take a cross product of two vectors, the magnitude of that cross product tells you something useful. Specifically, the magnitude tells you the area of the parallelogram created by those two vectors. So specifically, if you have two vectors A and B, like so down here, the parallelogram created by those two vectors is this, like this here. All right, so the cross product, the magnitude of that cross product tells you the area of that parallelogram. Really surprising how that works out. Now, again, there's various different ways that you can prove this. And again, I'm not going to go through this proof, and you're not responsible for this proof. But I do hope you'll take a look at it. This is actually a really neat one. What I like most about this proof, even though I'm not going to go through it, is that it's what I like to call a mathematical bank shot. That's a reference to billiards. I don't know if any of y'all ever played billiards. But the idea is that even though these are the two things that we're interested in, and I want to try to relate these to each other, and you would think that I would either take this expression and try to turn it into that, or that expression and try to turn it into this, but it's not. The way I'm going to prove these two things are equal is to start with something totally different and relate each of these to that. So, pretty weird proof, very creative, very clever proof, right? And anyway, I hope you'll take a look at it. It is very clever. But the most important thing here is make sure you know this result. Right there. Okay, so likewise, moving along. Next theorem, right here. Cross product has something kind of vaguely analogous to dot product. When the dot product is 0, that tells you some information about the angle between the two vectors, right? Namely that they're orthogonal, aka you're tempted to say perpendicular, and you remember all that business. So likewise, when the cross product is 0. Now, you're going to be tempted to say that the two vectors are parallel. And again, generically, that is what it is. But it's not. You always have to worry about the possibilities of 0. So the sort of the slightly more cautious, but generally speaking, suggestion of parallel is linearly dependent. And this is what's always true. So again, cross product and dot product. When either one of them is 0, you know something about what I'm going to loosely call the angle between the two directions. Worrying about zeros, of course, as well. Okay, so let's see here. Next result, and again, too bad we don't have time to go through these arguments. But this listing is, and I'm going to first state this incorrectly because that's the way people tend to think about it. This list is always in right-hand order, again, as people like to think of it. Now, technically, again, always the possibility something's 0. There is no right-hand order, et cetera, et cetera. But the strict statement here is that it's never in left-hand order. Generically, most of the time, anomalous cases with zeros being accepted, this list is always in right-hand order. Okay, so said differently, if you want to know which direction does the cross product point, a pretty good way to do that is, again, with your right hand, and just keep in mind how we define right-hand order. First vector index finger, second vector middle finger. Your thumb then points in the direction that would be required for right-hand order. We know that it is right-hand order, so the cross product points in the direction of your thumb. All right. Okay. Again, really clever proof. I hope you'll take a look. You're not required. It's not necessary, but cool argument. Neat ideas in there. Okay. There are, I've already mentioned this before, but there's different ways to go through all of the ideas that involve cross product and determinant and areas and lengths and stuff like this. Just a ton of different ideas that all connect to each other. Different books, different instructors like to go through this in different ways. I like to point out that what our book does, very different from what I've shown to y'all, right, is the book starts off with a geometric definition of the cross product. That's the exact opposite of what I did. I started with a formula, right, and then I, from that, derived some geometric properties. The book define, and by the way, not just this book, right, starts by defining the cross product to be the unique vector that has these three properties that we've just talked about. And it turns out there's always, no matter what A and B are, 0, not 0, whatever, all good. For any pair of vectors A and B, there's always exactly one vector that satisfies these three rules. And then they say, all right, we're going to define that unique vector to be the cross product. And then from these geometric properties, the book then goes through and derives the formula that I had started with. Right? So it's a different way of kind of passing through all of the ideas and connecting all the dots. And again, pros and cons. I like mine better. I think it's a little bit, I don't know, there's pros and cons to all of them. I find mine more geometrically satisfying myself. If you look and see how the book starts with this and then derives properties, what you're going to find is that there is a ton of opaque and unsatisfying algebra. And just crank. So I find that unsatisfying myself, but anyway. Okay. All right. Let's see here. So a couple other things to mention. Oh, yeah, sorry.
Question. I have a
Please.
notation question for the second one.
Yeah.
It says area and then 2 lines on the left.
Yes, thank you. Yeah, so this, I made a very passing reference to that a moment ago. So when we were talking about this theorem, this is that same notation. So this is a notation to indicate, so the two parallel lines says parallel, well, now that we got these two vectors involved, so you have to imagine what is the parallel thing that I'm talking about that relates to these two vectors. And so my idea is that indicates then the parallelogram. Yeah. Is that cool?
Yeah.
Yeah. Cool. By the way, I am not entirely sure if I may or may not have invented this notation. It seemed reasonable. I don't remember seeing it before, but I probably did. Anyway, I like it, so I'm using it. And then,
but if it's on both sides, it's length, right?
Yeah. Right. That's right. Yeah, exactly. Right. Okay, so let's see here. Moving. Oh, yeah, question.
So what exactly does that notation denote?
Yeah. So this notation refers to this parallelogram. Yeah. Is that satisfying?
Yeah. So that just means that you have another vector at the end of the
So the point is, if I give you two vectors like this, there's really only one parallelogram I could possibly be talking about.
Okay.
So that's the one. Yeah. All right. Okie dokie. So another result. A lot of people get comfortable with, all the boring properties of algebra, right? I don't know if they did this to y'all in elementary school, but they told me when I was in 4th grade that, now A plus B is always equal to B plus A, and this is important, and it's called the commutativity of addition. And I thought, wow, that's a big word, big phrase to describe the most obvious, ridiculously, pointlessly obvious statement. Why would we ever want to even talk about this, much less give it a big sounding name? And the reason why is because they were preparing students for the future in which there were going to be other operations that don't behave like you would kind of hope and expect, right? And cross product is one of those. And you all, of course, have had linear algebra classes, and you know likewise that matrix multiplication, not commutative, right? So we have to talk about boring commutativities so that it will be worth noting when there are surprising failures of commutativity. So this is one of them. Cross product is not commutative. However, you'll notice there is an equal sign in here. So something interesting happened. This minus sign is the fix. So even though the cross product's not commutative, it is exactly anti-commutative. And that's worth saying, right? That's an interesting observation and very useful. Okay. And again, argument, something to think through. Hope you'll take a look. Okay, lastly, and just to be explicit, now I've mentioned this well, I guess not quite, we have one more. But next to lastly, we've talked about cross product being linear in this sense, thought of as a function where one of the entries is fixed, right? And it's linear in the other entry. So we mentioned this on the first day of class. I believe there was a homework exercise in AHP that asks you to show that. Anyway, here's this sort of the final punchline phrased as a property, and that is this linearity looks like this property right here, which you'll see now, of course, linear combination on the inside, same linear combination on the outside, same thing either way, right? So there's the linearity, sort of, what it looks like. And you can see that I've got the, crossing with A, that's what T is. Right? So you can totally see how this is just exactly the statement of linearity. But it's nice to write it down as algebra. So this is algebra that is legal. And the way you're going to prove this, if you haven't already done that exercise, is to use previously established properties of the cross product, which is we already know that the cross product is additive. And we already know from linear algebra that the cross product is scalar multiplicative. Okay. By the way, and it works on both sides. So whichever way you want to use the linearity, totally cool. Alrighty, and then the last property to note, and it's another failure, cross product is not associative. So again, if you're kind of accustomed to high school algebra and just kind of blowing through, writing down algebra, whipping things around, just like, anything that looks like times must behave like times. No, it doesn't. Right? Easy landmine to step on. Accidentally forgetting that cross product is not like other, your previous products that you've seen. Not associative, so something to be careful with. All right. Okay, a couple of quick applications. We're not going to work any exercises on this, but I just like to point out when there are useful ways that objects that we're seeing show up in the real world. First thing I'm going to talk about is torque, and that is if you have an axis and something is turning on that axis, and like maybe you have a screw, right, that's screwed into a board, something like that. If there is what I'm going to call a lever arm onto which you apply a force, right? Then you can define, you can measure, how much turning power, how hard are you twisting that screw by way of this thing called torque, and it is measured with a cross product. So that's just intrinsic to the way physics works, and again, cross product is the thing that makes it make sense. Okay. Another, again, intrinsic to the world that we live in. This is just the way it is, right? When you have a charged particle, charged particle that's moving through a magnetic field. And let's suppose that the magnetic field is pointing like that. Then the movement of the charged particle cross with the magnetic field. So index finger in the direction of the movement of the charged particle, middle finger. A lot of people like to do all three of their fingers. I don't know, because it makes it look more like a vector field, I guess. In the direction that the vector field, the magnetic field is pointing, then your thumb, being the cross product, will point in the direction of the force that is being applied. So as this charged particle moves through there will be a force in this direction applied to it. Nobody knows why. This is purely empirical. This is just the way it is. Right? Nobody knows why gravity pulls down instead of pushing up. It's just the way it is, right? So likewise, now this is a weird one, but this is empirically just the way it is. And again, cross product, the perfect tool for describing that. How we doing? Everybody's good? All right. Okie dokie. So, all right, now lines and planes. I think, again, that hopefully y'all have seen at least some of this before. This is ultimately really linear algebra. Everything in here is linear algebra. There's not going to be any calculus in this section. But I am aware that some of y'all, either maybe it was a long time ago, you may have forgotten. I don't know. Your instructor in linear algebra may or may not have gone through all of this stuff, so I am going to go through this material. But hopefully this will be review. I'm going to start off with how to write down the equation of a plane. And if we're going to talk about a plane, we need to know something about the plane. So let's suppose that I have a vector perpendicular to the plane and a point that is in the plane. And I appeal to your geometric intuition. If I know the n and if I know the x naught, then that defines a unique plane. There's exactly one plane that goes through that point, and that's perpendicular to that vector. Yeah. Okay. All right. That being the case, I will notice that, let's see here, so again we have that point and we have this vector being perpendicular. Now let's ask the question, what would it mean if some unknown arbitrary point x were in the plane? Algebraically, what can I write down that I know is true if, in fact, some point that you give to me happens to be in that plane? Right? And the clever observation to make is that the difference vector, x minus x naught, would have to be parallel to the plane. After all, we're given that x naught is in the plane, and now we're presuming and trying to see what we can write down if x is in the plane. I have 2 points in the plane, and when I subtract, it's parallel to the plane. And of course, parallel to the plane. Now, let's see, let me erase, let's see, I'm going to try to clean this up as much as possible. Parallel to the plane means that those two vectors are orthogonal. Yeah.
If x and x naught are both points on the plane, why are they like vector?
Yeah, so I'm using the kind of the I like to blur the distinction between points and vectors. So now I do want to recognize points and vectors are different things. Points have a location. Vectors don't. Vectors have direction and magnitude only. Right? So they are different, but there is this very standard correspondence. If you give me a vector, there is a corresponding point, and vice versa, by putting the tail of the vector at the origin. Right? So, right. Okay. So as long as you let context be your guide, you can kind of blur that distinction and just don't forget the underlying reality. Right? But you can blur that distinction, and it's awfully convenient, because then that's half as many operations that I have to write down and half as many properties that I need to know. And it's just very convenient. So, yes, you're right. This is a point, x naught. I'm writing it as a vector because I could think of it as a position vector. But I want to think of it as a point, but I find the vector notation to be convenient in this case. And I also notice I need the vector operation, subtraction. So I need to think of these as vectors to subtract. So it's just slightly sloppy, very convenient, perfectly innocent convenience. Yeah. Good for everybody? All right. Okay, so you'll notice that I said orthogonal. Why didn't I say perpendicular? And the difference between orthogonal and perpendicular, again, is the possibility that one of these vectors might be 0. Now, here's the thing. I know that this cannot be 0 because its job in the first place was to be perpendicular, right, to the plane. It needs to have a direction. It doesn't make any sense to have that be the 0 vector. So that one's not 0. But what about this difference vector? Do we want to allow for that difference vector to be 0? In other words, do I want to consider, when the point x actually is the point x naught? Do I want that to be included? Said differently, is the point x naught actually in the plane? Yeah, it is. Totally. So I choose orthogonal, not perpendicular, because I do want to allow this to be 0, this difference. And orthogonality, not perpendicularity, is what allows for that. So this is just another example, and we talked through some of this last time or the time before, whenever. That you got to think carefully, depending on the situation. Wait a minute, is it perpendicularity or is it orthogonality? That's actually what I need, and the devil's in the details. And you just got to think it through, right? So every context, make sure to think it through. All right. Now you can just kind of move things around to get an alternative phrasing of this. I personally find that a little bit more appealing. No particular reason. I think it's probably slightly less pencil strokes, right, to write it like this. And then, if you're so inclined, you can take this normal vector that we were given, and let's presume that it has certain coordinates. And you can take the x vector that we're trying to test, and it has coordinates x, y, and z, and you can take this dot product and just crank it right out, and you get this. And then, of course, on the right-hand side, this dot product, n and x are both given, so if I know them, then I can literally compute their dot product. Then it's some number. Yeah?
Is that true for higher dimensions as well?
Yeah, actually, that's right. So you can do something. This will give you the equation of what they like to call a hyperplane in a higher dimensional space. Totally, yeah. And likewise for a line, if you're in 2 dimensions. Totally, yeah.
If the difference vector is allowed to be 0, then wouldn't that doesn't make sense to me, because wouldn't it be orthogonal to every single normal vector? It's perpendicular to the plane.
It would, but we don't. That doesn't matter, right? I mean, so this has been given. This is not allowed to change, right? So this is what's defining our plane in the first place. And so you are correct that x minus x naught would also be orthogonal to other things. That's got nothing to do with the fact that it is orthogonal to this one. And that's all we care about.
But then wouldn't it mean that it's wouldn't it be perpendicular to everything then?
Yeah. No, it'd be orthogonal to everything, not perpendicular. Yeah, because again, there's that nasty little distinction, right? So these words mean different things. So you are correct that other vectors could be in this position and it would still work if x and x naught are the same vector. But it's totally cool, right? That's just not a problem. Right. We're not saying that n has to be the only vector that makes this work. We're just saying this has to work. Yeah. All right. Okie dokie. So a neat thing to observe, and this is hugely convenient, if you encounter the equation of a plane written in this form, at a glance, you can just look at these coefficients. And that tells you your normal vector. So at a glance, you don't even have to do any work there, right? Just at a glance, you can just look and immediately see what the normal vector is for a given plane, if you have the equation for that plane. So very handy. We're going to be using that in at least one example today. 2 examples? Anyway, a couple of examples and plenty more as we go through the course. Okay, real quick then, let's use these ideas to find the equation of the plane that is defined by containing these 3 points. So the 3 points are given, and I want to find the equation of the plane. It's a puzzle. There's a bunch of different puzzles that involve being given some information about like lines and planes and stuff, and wanting to find other information about something related to that. And it's just an endless list of such questions out there. A good general rule of thumb is to, well, first of all, be aware of standard tricks, standard moves. Like if you're going to learn how to play chess, you need to learn basic tricks. You need to learn what a fork is, right? And if you're going to do these kinds of questions, you need to know certain little clever ideas and conveniences that other people have already figured out for us. So the trick that I'm going to show you here is that you can take this little scenario, subtract one of the points from the other two. Oh, those colors look kind of the same on this. Let me pick different colors. Subtract one of the points from the other two. Notice that those two difference vectors are parallel to the plane, and because these two difference vectors are parallel to the plane, I can conclude that their cross product must be perpendicular to the plane. That's a geometric appeal, right? If a vector is perpendicular to two vectors parallel to the plane, then where is it going to go? How could it do anything but be perpendicular to the whole plane? Does that make sense? Okay. Neat trick. Wish I'd thought of it. I didn't. Somebody showed me. Tool for my toolbox. Been using it ever since. Right. So, but this is a nice standard trick to have in your arsenal. All right. And once you have that normal vector, of course, it's all over because we can use any one of these points. Let's say A, doesn't matter. I can use any one of them to be my x naught. And now we just got through writing down a formula for n. And so we have the n, we have the x naught, we have the equation for the plane. Okay. Here's a neat fact. This comes up. It's not a deep fact, but it's a nice one to have right on the tip of your tongue. So here it is. If you have a plane, and if the equation has no y's in it, right? So if the equation for the plane, if the coefficient for y is 0, if that happens, and it does surprisingly often, okay, you get an immediate, free geometric conclusion, and that is that your plane must be parallel to the y-axis, like I have it drawn here. Neat fact. Trivial algebraic observation immediately leads to useful geometric conclusion. Okay. So why does this work? Well, it's no big deal. It's a matter of kind of thinking it through. Keep in mind, we already know that the coefficients tell me my normal vector, and it is perfectly clear, just looking at that 0, that that normal vector is perpendicular to the y-axis. And now I make a geometric appeal. If the normal vector is perpendicular to the y-axis, then the plane must be parallel to the y-axis. Everybody buy it? It's a real cool, real slick move. Again, something to keep in mind. All right, here is another example. This is another puzzle type question where we're given two things. Let's see, we're going to be given two planes, specifically the equations of two planes. And what we want to find is a parametrization of the line parallel to both of them specifically the line parallel to both that goes through a given point A. All right, so again, given two planes intersect to define what you might call a direction. I want to find the line that's parallel to that direction, namely parallel to both planes, but specifically going through that one given point. All right, so how do we do this? Again, I think a pretty good strategy in situations like this is write down what you have and what you need, and then try to think strategically about how you can get there from here. So what do I have? Well, I was given these equations, but I'm going to say that a little bit differently. I was given, effectively, then, these normal vectors. Right? Again, you can eyeball glance, looking at the coefficients, and immediately conclude what the normal vector is for that plane. So these are two geometric objects that I'm given. And let's see, what do I need? Well, let's see, I want to parameterize the line. I already have a point on the line. How do I parameterize a line? I need the point, which I already have, but then the only other thing I need is I need a vector parallel to the line. Right? So, and I haven't really done any real work yet, notice, but what I've changed an algebra question about, hey, here's some algebra, find other algebra. Now, instead into, here's a couple of geometric objects, I want to find that geometric object. Anybody see what I did there? And now, okay, well, how am I going to find this geometric object from that? And I'm just going to kind of think through, well, wait a minute, these two vectors, each of them is perpendicular to its corresponding plane. Each of these corresponding planes is parallel to this line. This line is parallel to this vector. That means I need for this vector to be perpendicular to both of these vectors. I still haven't done it yet, right? But that's my goal. My goal at this point is to find a vector perpendicular to two givens. And again, we already have that tool. That's cross product, right? Cross product does exactly that. So taking these two, whoopsie, wrong color. Taking these two given vectors and crossing them produces that parallel vector that I need. Everybody happy? Okay. Excuse me. Okay, let's see how we're doing on time. Yeah, okay, cool. Okay, so I have a warning. Just something to be careful about, something a lot of students inadvertently, accidentally screw up. I like to call them landmines. And that is to be very, very careful with transitivity arguments. And what do I mean by transitivity? What I mean is, if you can connect one idea to another and another to a third, then you would think that that would imply some connection that sort of crosses both of them and connecting the first idea to the third idea. Right? So, for example, in this first example we talked through, I started off by observing a relationship between the plane and the normal vector, and then I concluded also a relationship between the normal vector and the y-axis, and then from that, using the picture, I then said, oh, okay, well, then I guess we must have a relationship here between the plane and the y-axis. So this is an example of what I'm calling a transitivity argument, right? I know the green relationship, I know the blue relationship, therefore I get the purple relationship. Okay, fine. And that works, and that's fine. There's nothing wrong with that. In this one, kind of likewise, I started off knowing that, let's see here, that these vectors were perpendicular to these planes, and I geometrically argued that these planes have to be parallel to that vector, and then I concluded that there must be a relationship between these given ends and this v, namely that these must be perpendicular to this. Again, a kind of a transitivity. Right? So I say be careful with this. I mean, I'm not saying don't do it. I love these things. These kind of arguments are extremely useful, right? But just be careful, because not everything that kind of on paper looks like it ought to work actually does, right? So it's very tempting, for example, to look at, hey, what if V is parallel to P and P is parallel to W? Wouldn't you want to say, doesn't it kind of scream, well, then V must be parallel to W? It's very tempting if you don't think it through carefully, right? But check it out. No, it doesn't. V is parallel to P, P is parallel to W. V and W are not at all related. So heads up, be careful, think it through, right? Okay, likewise, P is perpendicular to Q and Q is perpendicular to R. It's going to be tempting to think that P and R must have to be parallel, maybe, or something, or maybe they're perpendicular, or you'd think there'd be some way to kind of connect the dots there. But nope. Again, no particular relationship necessary between P and R. Everybody see what I mean? So, like I say, be careful. Okay, now my rule on this is rather than me enumerating a complete list of all possible hopeful relationships, transitivity relationships between like lines and planes and vectors and oh my gosh, there's just so many of them that would be tempting to, which one's parallel, parallel and perpendicular implies what, and perpendicular implies what, and there's too many. Can't possibly. Right? So the rule on this is going to be as follows. You can cite transitivity rules, you just have to be right. Right? I can't document them all. But if you cite, if part of your argument suggests effectively that this and this imply this, that's wrong. It just doesn't work. So heads up, it's on you. Think it through. Make sure that you're right before you use such an argument. Okay, pausing. Questions? Is everybody happy? Okay. Let's talk about how to parameterize a plane. The only parameterizing we've done previously were curves. So again, what's the idea of a parameterization? The idea is that it is a point generator. So I want to be able to generate every point on this plane. And first I'm just going to argue that what I'm going to need to do that, well, I'm going to need a starting point. I can't generate points in the plane if you don't even tell me where my plane is. Right? And I claim that I'm going to need a vector parallel to the plane, and I'm going to need another vector parallel to the plane. Not parallel to the first one. And with that, I claim that I have all the tools that I need to generate any point in this plane, because V basically gives me the ability, I can just go kind of, if you will, in the V direction by, some amount, perhaps longer, perhaps shorter, perhaps backwards. S would be negative if I went backwards there. Right? That allows me to go as far as I want in this direction that the plane points, and then multiples of W allow me to go as far as I might want to go in the other direction. And just choosing my S and T cleverly, I can get then to any point in this plane. And again, the big idea is you just start with the point you're given, go, here it is, as far as you need in the one direction, as far as you need in the other direction, and that will get you to any point you want to get to. Yeah?
Do V and W have to be perpendicular? Or
Nope. They can't be parallel, but they don't have to be perpendicular. Yeah. So as long as V and W span the plane, you're good. Yeah. Everybody good? Okay, so neat fact. Super quick example. If you want to parameterize a plane containing 3 given points, you're going to notice these are the same 3 points we talked about before. Copy, pasted the picture and everything, right? So this is just like that earlier example. And if you want to parameterize this, then you can use any one of these points as your x naught, right? And then subtracting that from the other 2 gives you your direction vectors, and then citing the formula from the top of the page. There's the parameterization. What do you think? Everybody happy? Okay. Distance problems. There's various versions of computing distance. We'll start off with how to compute the distance from a point to a line. And let's see here. So if I have a point given, and if I have a line given, how would I compute this distance here? Like that. There's actually a couple different ways that you can do this. One thing you can do is take the point that you're given. Now also choose any point you like on the line. Doesn't matter. Whatever. Any point that you want. Now, what you cannot do is just claim that distance is the distance in question. Obviously not. Now, when we say that we want the distance from a point to a line, it's understood that I mean the shortest possible distance, right? If I'm out in the ocean and I want to know how far am I away from shore, I mean, obviously, how far am I what is the shortest distance to shore? Technically, this is the shore too, but that's not what I'm talking about when I say how far am I from the shore. I hope that makes sense, right? Is that clear? Right? You always want the perpendicular distance. You want the shortest possible distance. So, okay, but what you can do is take that vector and then compute its projection in the v direction. And once you have that projection, notice then that this difference, I'm running out of colors. Okay, I guess I can do this no, I guess I already have this in blue. But notice that this difference orange minus red is going to give you that blue vector. And then, of course, all we need is the magnitude. Wrong color. The magnitude of that blue vector. Yep.
Yeah, for that vector for D, why do you use projection as opposed to like the component?
Because I need to do a vector operation. It's a great question. I need to do a vector operation here. I need to take this vector minus that vector because that works, right? In other words, I can take a vector minus a vector, and that gives me a vector. But if I take like this magnitude of W and the magnitude of the projection, namely the component, right? The difference of those magnitudes, the difference of those scalars, does not give me that scalar. So the geometry just doesn't work. So does that make sense?
Yeah, that makes sense.
Yeah. So that's right. So you got to think about what algebraic operations do we have that emulate the picture that we need to understand. Yeah. Good question. Yes.
Why do you even need the projection? Because I'm trying to think like vector geometry. Sometimes you just have pictures and you can kind of do like one minus the other to get the other side.
You might get lucky, right? But the point is you can't assume it, right? In other words, if I were to just say, let's see here. Well, let me just do like this. If I were to just say, well, here's a point that's on the line, and here's the point I want to know how far it's from the line, and if I were to just straight up compute that distance alone, it's just not what I'm interested in. It gives me an answer to a different question, right? So what we have, the role the projection serves is effectively to point out exactly where is that nearest point. And once I know what that nearest point is, well then it's just a matter of computing distance. Is that cool? Yeah. Everybody happy? Now here's a different move that you can pull. Kind of nice. This is another little mathematical bank shot. We're going to start off, same picture, right? So we've got a point and a line and the projection, et cetera, et cetera. I'll just point out that even though the question was about distance, this area is something that I can compute two different ways. And kind of like we saw with that example that I didn't go through the details of, if you can compute something two different ways, then the two different answers you get must be equal to each other. And that's a foot in the door to compute stuff sometimes. It's surprisingly often. Right? So on the one hand, I can compute that area as height times base. On the other hand, I can compute that area as the magnitude of a cross product because, well, that's one of our brand new known cool properties of the cross product, is it gives me the area of the resulting parallelogram. Now, okay, who cares? I have two different answers to a question no one asked me. Right? We're interested in distance, not area. But then you notice that the distance that you're interested in is part of that relationship. And so knowing that these two things are equal to each other, because they're both equal to the area, allows me then to solve for that distance. And it turns out, in fact, I don't even really care about the area, but now I have a formula for distance in terms of things that I've already computed. So, slick move. Neat. But sometimes this idea is really, really handy. Okay. All right. Oh, I'm sorry. I just looked at the clock and realized it's 11:05. Let's see. This class ends at 11:05. Is that right? 11:10. Oh, good. Okay. All right. I'm sorry. I lost track. Okay. Awesome. Fantastic. Okay. Couple of more examples that I think we can squeeze in here. What if you have two parallel planes? How would you find the distance between these parallel planes? Now, again, I emphasize distance between two planes. There's a bunch of different distances that start in one plane and end in the other plane, and that's not what we're talking about, right? Distance means the shortest possible distance, right? From any point in one plane to the nearest point in the other. So you do have to be very careful in these kinds of questions and make sure that you're clear on exactly what geometrically represents what you're looking for. So the neat observation to make here is that you can just pick any point in each plane and subtract. Realize that you already have, by knowing the equations of the planes, you have a normal vector to the planes. And then check it out. The distance that you want just happens to be, I'm going to loosely say, the component. It is, it's how much is that purple vector pointing in the orange direction is the distance. And then asterisk, okay, well, fine, technically, components can be negative, but we were asked to compute a distance. Distances can't be negative. So you just have to recognize that component gives you two things. It gives you the distance, but it also gives you some indication of whether you're going the wrong way or the right way, or not that matters, right? So you just have to throw in the absolute values. So do be careful about that little micro detail. If you compute a distance as being -4, that's not good. So don't forget to take the absolute value. Yes?
Why A and B, they're points.
Yep.
Correct? Why
yes.
they have a vector sign?
Right. Again, so I like to blur the distinction for algebraic convenience. And just keep in mind, whenever you have a point, there is something called its associated position vector. Right? That's the vector that whose arrow goes from the origin to whatever that point is. Right? And using that association to blur the distinction saves me tons of trouble. So, for example, you notice there's a formula for how to add vectors. Did you notice that there is no formula for how to add a point in a vector? Because it's the same formula. Right? If you just interpret the point as a vector for that purpose, and it's geometrically natural because if you have a point and a vector represents a displacement, then again that's geometrically a natural thing. So yeah, so we it's convenient because we blur the distinction. The responsibility then is that you always have to be very careful to interpret as appropriate as required. Okay, good place to end it. All right, we'll pick up here next time. Y'all have a great weekend. See you later.
Thank you.